Hi there, I'm Jim, one of the solutions engineers for Edge Impulse, and today I'm here to take you through really simple workflow demonstrating how a customer might go from zero to a fully working deployed model on one of our supported boards in under an hour. So what I've got here is a little fan in a case with one of our supported boards, the Arduino Nano 33 BLE Sense, mounted onto it. And this board is fully supported by Edge Impulse and has an IMU on it which will collect accelerometer data for us today, and we're going to try and do some anomaly detection with this. So here I am in Edge Impulse and we're going to create a new project. Okay, so we're in our new project and we want to collect some accelerometer data. And it's really simple with fully supported boards for an end user to connect their device and collect data from it directly within the GUI. All we need to do is go and find the officially supported target, which in this case is the Nano 33. We can head over to GitHub and download the firmware for this board, which I've done already. If we go over to terminal, list the files in the folder, you can see the Arduino build bash script is in there, and that just does everything for us. So all we need to do here is have the board connected, select bootloader mode on the board, and then just run Arduino build.sh and then flash. And all of these instructions are in our documentation, so it's really easy for the end user to get set up on their own without any support. Okay, so we flashed the data collection firmware onto our Nano board, and what this allows us to do, really simply, is to now run the Edge Impulse command line tool, Edge Impulse daemon. Just highlight that for you, and I'll just clean it so we've got a clear idea of what a new user would see. So all you need to do is enter your email address for your Edge Impulse account and your password. It connects to your board and you can choose the project you want to connect it to. Give it a name. We'll call it Nano Anomaly. And if we head over back into Edge Impulse, all we need to do is go to our data acquisition tab, and you can see the device is already here, ready set up. So with this setup, we want to start off by collecting some data for the normal states that we'd expect to see with a fan like this. So the simplest ones are off, idle, and nominal, so with the fan running, but nothing's wrong. So I'm going to go ahead and show you how to do that really easily with our Edge Impulse toolkit. We'll start off by collecting some idle data. And we're going to collect a 10-second sample from the inertial measurement unit, and we're going to go for the highest frequency available from this sensor set, which is 100 Hz. It's good to start high because you can always downsample, and Edge Impulse allows you to change the sample rate really easily later on. So what I'm doing now is collecting the idle data, and we're going to collect about 2 minutes of this data. It's a good starting point, and then we'll collect some nominal data for the fan running in a second. Okay, so we've collected 2 minutes of idle data, and you can see that the data acquisition dashboard shows a really nice readout of the data that you've just collected. You can look through all of the samples and see that there's nothing anomalous in there just by eye. And you can see your test and train split and how much data has been collected. It makes it very simple to collect data for a first-time user. So now we're going to change our label to nominal and turn on our fan and collect some data for just normal fan usage. Okay, so we've collected 4 minutes of data, 2 for each state, and now the important thing is that we collect some data to test on as well as to train. So if we just go into our test data window here, then we can collect some more data for nominal and idle, and this will be unseen to the model training process so that we can then test at the end of the process whether or not our model is going to be accurate on real-world data. So I'm just going to collect some data for both states for testing purposes, and I'll be right back. Okay, so now we've collected some test data as well as our training data. Now, collecting data directly from a board like this is not the only way that we can bring data in to train our model on. If you have an existing data set somewhere stored like Amazon S3, then we can import that data really easily with the Enterprise Toolkit and take the labels of that existing data and pump it straight into our model. I won't show you that now, but we'd be happy to show you in another video if you're interested to see how that would work. Now that we've got our data, we can design our impulse. I'm going to start with a window size of 500 milliseconds and an increase of 200 milliseconds and keep the frequency as it was when we recorded. And then for the processing, I'm going to add a spectral analysis block. This is really good for repetitive motion, such as a motor or a fan in this case. So we've got our spectral analysis block here, and while our edge device has an IMU which collects gyroscopic data as well as magnetometer data, we're going to focus on the accelerometer today, just to show how simple it is with one sensor to come up with a working model. But you can use a feature called sensor fusion within an edge impulse to combine different sensor outputs to get a new outcome from the data that you've got. It can be really powerful. So learning blocks wise, we're going to start off with classification, a neural network classifier that will help us determine whether the fan is in idle or nominal states, and then in the future we can add new classifiers in for anomalies that we find with our second learning block, which will be anomaly detection. And this will work alongside that classification to find anything that doesn't fit into those original classifiers. This is a really powerful way to create a model that can do anomaly detection without having anomalous data to start with. So in this case, so far we've only got idle and nominal working data. We don't have anything new yet, but we can see how we can add that in at a later date. So we'll save that impulse and go into our digital signal processing block to just set the parameters and generate our features. So you can see here we can go through any of these samples, and you can see the DSP results after the filters and the spectral logs. And you can also see an estimate for the on-device performance, which is a really powerful way to see if your processing block or your learning block is going to fit on your edge device. And Edge Impulse does a huge amount behind the scenes to make sure that that happens. So we'll save these parameters. The default are usually good for a simple model like this. And we want to calculate the feature importance. This is important for the anomaly detection block. This will tell us which aspects are contributing to those original classes, and then we can make sure that those are the ones we focus on when we're looking for anomalies. So we'll just generate these features. Okay, so we've generated the features, and as you can see in the Feature Explorer, which is a really useful tool for just doing a sanity check on the data that you've got, we've got really clear separation between our idle and nominal states here. So all of our samples, which are broken up into 200 millisecond chunks, appear to be nicely grouped between idle and nominal states. And then our feature importance, we can see that it's mostly the z-axis that is important and between particular frequency bands for detecting these states. And we'll see how that factors into the anomaly detection feature later on. So we're going to move into our neural network classifier. We'll balance the data set, but generally the initial settings for the neural network work well for a simple model like this, so we'll leave them as is. But you can go into much greater depth with your neural network model or a custom model if you want. You can change the neural network architecture here, and you can even go into an expert Keras mode where you can manually edit the Python code that runs behind the scenes. And if you have a model that you have in your tool set already, you can import that into Edge Impulse and run your run your model within our platform, so you don't have to just use the ones that are built into the platform. It's really powerful. So we're just going to start training on this. Okay, so we've trained the model on our idle and nominal states, and you can see we've achieved very high accuracy here. Nearly all of the samples were correctly detected, apart from 3 idle samples, which is probably due to something knocking on the table. And you can see our on-device performance is really good. It doesn't use much flash or RAM, and the inferencing time is almost instant. So you could happily run this alongside another application on this edge device. So moving on, we're going to go into our anomaly detection model now. And we're going to select the suggested axes. These are the ones that came up when we were doing feature generation earlier. And we'll start the training. And what we've done here is run a k-means clustering algorithm, which creates these windows around our existing data. And if we introduce new data that doesn't fit into those windows around the existing classified data, then it will be given an anomaly score that is higher than expected, and then it'll be flagged up, that sample, as an anomaly, which allows us to find anomalies in data which we didn't know was anomalous before we started collecting it. It's really powerful for something like an industrial application such as motor monitoring. So we can move into the live classification window here, and I can show you in real time through the Edge Impulse CLI, collecting data from our device, that this model works, not just in theory. So I'm going to change our sample length to 1 second. We've got our device connected here, and I'll just take a sample of the idle, and we'll see that that classifies correctly. So you can see here that there's a 100% score on the idle there. I'll just label that as idle so it comes up in our testing data later. And then we'll do the same with the fan on and see that that works. So there we go, that's 100% nominal. You can see that fits that sample really nicely within our nominal area and our spectral features, so as expected, it works. Now where things get interesting is when we start to introduce an anomaly that we haven't trained the data set on. I've got a screwdriver here, and our board is mounted to a little barrier cage. So if we loosen these screws, we'll introduce new vibrations into the system. And I want to see if, by loosening these screws, we can detect that as an anomaly in our current data set without having to retrain our model. Okay, so we've loosened those screws. Now we can see what happens when we take a new sample with the fan on from the live classification window. Okay, so here we are. We've taken a sample from our device with these screws loosened, and all three of the samples of the 1 second have come out as anomalies. Now that's really interesting, because what that means is going forward we can now take more data with the screws loose, knowing that that's an anomaly and knowing the label of it, which is, screws loose, and then we can retrain our data set on that anomaly. So what I'm going to do is label this as anomaly loose cover. And what we want to do now is go and retrain our model with that new anomaly introduced and see if we can't then detect that more accurately going forward. So go back into our data acquisition, to our test data, and I'm going to collect a good amount of data of this new anomaly that we found. Okay, so we've collected some more anomalous data there for that loose cover plate scenario. And what we're going to do now is try and classify all of that test data. So the machine learning model and the anomaly detection model have not seen this data yet. So what we're expecting is that our initial data, our nominal and idle data, gets classified correctly, and that these new labeled anomaly loose cover samples come out as anomalies in that data. Okay, so we've finished testing all of that data, and as you can see, these samples here, which we've labeled as anomalies, have come out with really strong anomaly sample labels, whereas all of our nominal and idle testing data has come out with pretty much all idle and nominal expected outcomes. You can see that even better in our feature explorer down at the bottom here. So these are our correctly labeled idle samples, correctly labeled nominal samples, and then over here these grey samples are our loose cover anomalies. So what I'm going to do now is retrain our model, now that we know that our model's correctly detecting these anomalies, with our anomaly loose cover samples included in the training data set. And then once we deploy, what our board will be able to do in the field is detect idle, nominal, and those loose cover samples, as well as being able to detect new anomalies on the side. So that really is simple. All we need to do is go here, back to data acquisition, to our test data, select our loose cover anomaly data samples, and then move them to our training set. And then head over to Retrain Model, click Train Model, and this will go through all of those steps that we did earlier, generating the spectral features, generating the neural network and the anomaly detection model, and then out the other end we'll see that final accuracy result. Okay, so we finished retraining the model, and you can see in the neural network with this new anomaly that we've classified as the loose cover, we've got really good separation down here and 100% accuracy. So this bodes really well for when we deploy on the edge device. So we've still got the anomaly detection model as part of this pipeline, which still means that any new anomalies that we introduce that don't fit within those earlier classifications will get flagged up as anomalies. So what I'm going to show you now is how to deploy a model onto your edge device. So Edge Impulse comes with a number of deployment options. You can create a library which can integrate with all sorts of different programming languages or platforms, and that can allow you to create a custom program that integrates your model directly into your own workflow and algorithms. But we also have ready-to-go firmware that's pre-built for supported platforms. That makes it really simple to deploy your model directly onto your edge device and see how it performs. So that's what we're going to do today. I'm going to select our Arduino Nano 33 BLE Sense. So now what we're going to do is just click Build, and this generates a binary that can be flashed directly to a supported board or loaded into a supported platform. Makes it very simple to run that impulse on the edge. Okay, so we've built the firmware, it's downloaded, and I'm just going to extract it and show you how to flash it. So flashing the firmware is as simple as making sure that your Edge Impulse daemon is shut down, putting your device into bootloader mode or preparing it to flash, finding your firmware, and just running the flash command. Okay, there we go. So the firmware is now flashed with our model on the edge device. So now to see that live classification working on the board, we just need to do one simple command with the command line. Edge impulse, run impulse. What this does is connects over serial to our device which is already running the model on it. And then shows you live classification in real time of whatever it's detecting. So every 2 seconds it will run the inferencing model. So at the moment you can see really simply that we're getting a strong idle score of 0.996 because the fan's not running. When we turn the fan on, so we get a really strong score of nominal fan there and a low anomaly score, which is really good across all these samples. Now what I'm going to do is loosen our cover as we detected earlier as an anomaly. So our cover is now loose, and I'm going to start the fan and we'll see what happens. So there we go, with the cover loose and the fan on, we got a really strong score for the anomaly there. That's proved out what we expected to see, and that is running directly on our edge device. Now, once I've tightened this back up, we can introduce one final anomaly which has not been yet classified by our model. In this case, I've got a piece of paper here, which I'm going to put into the fan blades to simulate a blocked fan or something in the airflow. And this has not yet been classified by our neural network model, but our anomaly detection model, which is still running alongside that, should be able to see what's going on there. So we're looking at the anomaly score here, I'll just turn the fan on and place my blockage in the airflow. So what we see there is a strong anomaly score of above 1, which suggests that all of these classifications may not be right and that there is an anomalous classification there which is outside the scope of the ones that we've already detected. And that's really strong. So what that could tell you in the field is that you need to look at that sample of data, get a human expert involved to label it to see what's wrong with the machine. Either go and fix that, or you can take that data and put it back into your model to allow it to more accurately detect new anomalies. So in that case, what we might do is take some samples of that anomaly, put it back into our model, and label it as blocked fan anomaly. And then in the future, you'll be able to detect the blocked fan separately from your loose cover plate and separately from just general anomalies. So what I hope I've been able to show you today is that it's really simple for an end user to go from nothing to a trained model that runs on the edge in under an hour and get some really good accuracy results out of it, and also show that there's a lot of scope to grow from something simple like this into a full workflow that could integrate existing data and that could be retrained in the future. I hope this has been a useful walkthrough of that workflow for an end user. If you want to see any of the more advanced features or have any more questions, do get in touch with the solutions team. Thank you very much for watching.